Okay, I've got 3 o'clock, so let's go ahead and get Bill's talk up, and I'll introduce him. So our next talk is going to be from Bill Nesmith at JPL. So he's in their thermal energy conversion and systems group. So he does space-based laser power beaming, also with lithium-ion propulsion systems. So he's got a lot of experience, and he's going to tell us some more about power beaming for deep space, as well as their work on power beaming for permanently shadowed regions. So Bill, if you're there, you can come off mute and take it over.
Okay, that sounds good. Can you hear me okay?
You sound great.
Good. The other thing I'll ask is, can you see me okay?
Yep, I can see you and hear you. Pictures loud and clear.
All right, that works great then. All right, then, since I guess you have the charts, then I guess what we'll just do is that whenever I want to go to the next one, I'll just say go ahead and change it.
Yep.
So I guess to get started here, the power beaming for the deep space and permanently shadowed regions is a topic I'm going to cover. This work was done with a team of us from JPL, and JPL is the Jet Propulsion Laboratory, which is a NASA laboratory that is being, I guess, operated by the California Institute of Technology. And let's go on. The other members that were working with us certainly were the folks at Silmar, that Spectral Lab. The folks that were supporting us there at JPL were Jonathan Grandidier, Malcolm Wright, John Brophy, and John Elliott. And Dimitri at the Boeing Spectral Lab was one who provided a lot of the information for our presentation. So if we'll go to the next chart. On chart 2, we're looking at kind of a brief outline of the objectives that we're going to be addressing in the presentation. We'll discuss some of the technologies and what power beaming facilities there are at JPL, both old and new. And we'll be looking at some of the indium gallium arsenide device results in particular, as well as looking at comparing some of the solar photovoltaics systems with the power beaming, and look at some of the examples of some of the end-to-end power systems that we're utilizing for the systems that we're looking at for these space applications. Next chart. Under the objectives, we're showing what the components are that really make up an entire power beaming system. And you see here, certainly we have the electrical to optical conversion that has to take place. We have the transmission through the medium, and then certainly the optical to electrical conversion systems going on there. One of the things that we were involved with a number of years ago was doing some of the laser power beaming up at one of our facilities, and it was one regarding the transmission where we had a forest fire in Southern California, not that uncommon, but in this particular case, the forest fire actually interrupted our laser testing, and we had absolutely nothing to do with the fire. So we're completely innocent in that department. We continued to look at some of the various technologies that are going to be involved in these applications. We look at the overall, the end-to-end power system characteristics, and determine the best solutions and how these solutions may change as the mission applications, the separation distances, and the technologies tend to evolve. And so you see here kind of a breakdown of the assessment of all of the different types of laser power converters that are out there, and we'll look in that more a little later in the next few charts. But you can see that certainly we should always start small and then work up, and hopefully we would be doing the same thing here, starting with the shorter distances so that we get some good surface to surface power beaming, even as we have done in terrestrial tests and application. And certainly there are things where it's very conducive to have things, particularly at the Shackleton crater on the moon, where you could be beaming down into that permanently shadowed region. So it's nice that it's permanently shadowed, because that makes the water ice there available for us to hopefully be able to utilize when we get human beings there as a hydrogen, oxygen source, water for drinking and other applications. And the longer the distances are, that as we go up for things that are maybe in the more midterm, powering the landers and the rovers and the orbiting systems from various locations in space. And finally, what we're really looking at is that a very high power beaming at large distances really represents a game-changing possibility for getting spacecraft out into deep space. So what we can hopefully get done with that is an improvement in power beaming as well as the lasers, but also we are looking very hard at lithium-ion propulsion systems that could also fit into this and help even more in this regard. Okay. Next slide. What we have here, it kind of documents the technology and past experiences, as well as a lot of the future mission applications that we'll be discussing. Certainly NRL had done some of the things here for the 400-watt system components here, and as well as some of the transmission distances, 30 meters and 200 meters. I was very pleased to hear that a lot of the RF work that JPL had done earlier was reported in earlier presentations. So that's always nice to see that that's actually being tracked and followed. And I actually had the pleasure of working with Dick Dickinson on some power beaming things after the RF work that he did there at the laboratory. Next slide. What we have here provides an example of kind of the end-to-end designed process that we've kind of gone through for concept for 2 of the lunar missions, and with the kind of brief descriptions of their efficiencies of each subsystem and some impacts that each one of these subsystems has on other subsystems. So if we look at power beaming concepts here, where we are looking at for possibly charging some of the small robotic power systems located in these permanently shadowed regions that, like the Shackleton crater we talked about, that certainly enables a lot of possibilities in other moons or possibly even planets where they are finding ice in various locations. Certainly the providing power to some of the future lunar bases would be a big plus, as a way to try to handle that 14-day, 14-night cycle that we're tending to have to deal with on the lunar, particularly when we are dealing with things that are more equatorially mounted. Certainly things improve when we go to places like the South Pole, where we currently have Shackleton crater's icy content in the bottom of it, make it a real possibility for us to have a reasonable base to work from for humans. And again, you see the layout there for they have the emitter, the laser, power beaming, and then the receiver, and all of the power conditioning and stuff that has to go on with that. And when we break those down into some of the subsystems, like the laser optical elements, where you have also the thermal management, as well as the laser power converter and power electronics, we're also trying to push the technologies in these different areas. And certainly anything that we can do, say, to make the systems more efficient makes other things like thermal management much easier. So the issue of always having to reject the inefficiencies or waste heat in these things makes it more and more challenging, and certainly view factors, areas, and mass, things that you have to deal with, as well as dealing with some of the converter technologies and trying to push those up to higher and higher levels, as well as going to some of the shorter wavelengths for some of the spacecraft power systems. And finally, we are trying to push in the area of the power electronics, the gallium nitride based conversion systems, because that tends to help all of our spacecraft, and we might as well take advantage of all of the other technology developments to make it as easy as possible to accomplish our mission objectives. Next chart. Here we have a basic summary of both the mass and power of one of the mission concepts that we were looking at. And certainly the particular chart here is just an artist's conception of what we're looking at, but it provides you kind of an idea, with the Earth in the background and a lander near the edge of the crater and beaming it down below, breaking down each of the systems and subsystems by kind of their mass, showing things that are generally in the 10 to 20 kilogram category, to be able to beam down to a receiver located on kind of a simple rover that would be down at the base. But certainly that looks like one of the best options we might have as a way to explore and determine what kind of resources are actually available at the bottom of the craters. So it's a way for us to get the beam power down there to power the rover and actually get, we'll call it ground truth down there where the water ice is located, so that we can take advantage of it. And at least this is a starting point in terms of the mass breakdown we've been looking at so far. Next chart. Here we're looking at a comparison of a solar photovoltaic system versus a power beaming system. And one of the things that we see here is it compares those for 3 different types of missions while beaming from 2 different locations. And in other words, whether it's located on the lunar surface or from space down to a lunar location, whether that's a Lagrange point or whatever. But anyway, this was trying to show what aspects in particular could be mission enabling. And even in the case where they were looking at using the solar in a continuous power producing application, the real concern or problem with it was also that you still needed to carry a lot of thermal energy storage, because you're talking about something in the order of 336 hours of chemical energy storage to that comes as a result of that. So that is always going to be, I think, a real tough challenge to try to use and utilize the resources that we have and that we can deliver to the moon to deal with that 14-day night cycle. So certainly these things do seem, in terms of feasibility, to be falling in the categories of possible, and certainly the power beaming, assuming like 1 kilowatt laser and various wavelengths and a 1 square meter system, is what's really being addressed here. And the photovoltaics here going to the efficient, 32% efficient solar cells, and as compared to when you have a really well-tuned PV array in conjunction with the laser, you're getting something closer to the 65%. So we'll be looking at some of the other PV cells and their efficiencies in the laser beamed power beaming environment also, and their efficiencies. Next one. What you have here is a picture of one of the JPL and most recently developed test facilities. It's an indoor test facility here that that has been developed, and the key point here is that this newer indoor laser power beaming facility should not be confused with the optical communications laser labs that we have, because JPL have for some time been trying to see and develop ways to communicate with the spacecraft in as efficient way as possible. But here, we're certainly focusing more on power beaming. So this one is much more power oriented, and thus we're doing the testing of the various PV cells in this facility. But we also shouldn't confuse it with some other facilities. JPL also has the Table Mountain laser facility that's been used in the past, and certainly some of the military people have funded some testing that we've done up in that area, as well as the JPL, as is discussed earlier, outdoor RF facility at Goldstone Dry Lake Bed. So that certainly is a part of the JPL Deep Space Network, as well as the other facilities that we have at a couple of other locations around the world, in Australia and around Madrid, Spain. The next chart. It shows kind of the expected efficiencies of the various cells that certainly we have been working with Spectral Lab to try to come up with lasers, as well as the photovoltaic converters that are well tuned to fit it. And you can see here we're showing the various efficiencies in conjunction with the various wavelengths of the lasers and the different band gaps that we're dealing with the different combinations of the materials that we were looking at for the photovoltaic conversion systems. And you just see a rundown there on the right side of all the various ones, as well as the numbers associated with each of the wavelengths that were analyzed for it. And it's to me very impressive that we have things there that are predicted to exceed 60%. So I find that very encouraging. Next slide. What we have here is a kind of a plot of the spectral response as a function of the wavelengths for both the gallium arsenide and the indium gallium arsenide band gaps. The certainly wavelengths here of the 808 nanometers, well matched, with the room temperature, and the gallium arsenide band gap to the 900 nanometers. You can see here the plots with the lasers, and then you can see how each one of them then tends to fall off at the various wavelengths. And again, this was provided by Spectral Lab with the 4 lasers and the 2 different band gaps being addressed. Okay, next one. Oh, this one is, yeah, that's fine. What we have here is the gallium arsenide dual junction device that we had originally tested at our new facility, the newest indoor facility there at JPL. And here you can see the IV curve as well as the efficiency curve for the various levels of power beaming. And you can see here from the data that you've got a pretty substantial drop off. And we did a pretty good job of mapping all of it, and determined that these were actually very real drops off in terms of there was a large series resistance that was in there. And so we said, well, that should definitely be a fixable problem. And it was. And in fact, if we go to the next chart, you can see here we're looking at an indium gallium arsenide one with a laser power converter. And we went to a much larger area, better integrated contact for it, because it was actually the contacts, essentially external contacts, that were just adding a resistance to the circuit and essentially burning up a lot of the power that was being generated by the laser to the cell and then the output. But it was encouraging that this would be a very fixable problem, particularly in documenting here what the wavelengths are for it. And if you go to the next chart, you'll see here that that's an indium gallium arsenide device with the 808 nanometer laser has a much nicer IV curve, something much closer to what you'd expect to see in a good photovoltaic system. And so with the currents and the powers all shown there, you get something that looks very reasonable and very hopeful in terms of making some real devices that can be and are tested in the laboratory and getting results that are able to produce these kinds of curves, as well as it's nice to have the lab so that you're able to identify problems like the one that we were able to identify here with a particular metallization that was going on, let's say, externally to the cell itself. Next slide. Here you can see also the efficiency curve for that same indium gallium arsenide device. And so it's very encouraging that efficiency stabilizes out around the 30% level. And that's certainly with the 1064 laser, and certainly expected efficiencies in the 46% is very encouraging. Next, here we have the power density being shown here at a very impressive and high level. So the power density being plotted with the overall power beamed. You see that for the indium gallium arsenide device, the highest measured power density got us up to the 12.14 kilowatts per square meter. And this corresponds something that, about 30 times what you would get from just a regular solar array at 1 AU. Next. This is an activity that a number of us, including myself, were involved in at JPL. And this was one of the NIACs, one of the NASA, advanced innovative concepts. Here we were looking at power systems where we could actually put the arrays in kind of an optimum location in space. The laser, an optimum distance in particular from the sun to get maximum performance in terms of temperature and stuff. And certainly we were pushing the state of the art in terms of what are our options for getting very large area arrays out there with a very low mass. And so we looked at all kinds of concepts, including inflatables with like Lagardes, very lightweight systems there, things that looked almost like wheels with spokes, and then being able to put these deployable systems out there. JPL has worked with Lagarde for many years and all kinds of different inflatable concepts. But we were also teaming up with Caltech because they had a number of people there that were focused on trying to look at beaming power from space back to Earth. But certainly our interest was much more just getting it up out of the Earth environment, so that would really free us up to use just about any laser that we could in deep space. And particularly with JPL's charter being more of planetary exploration, using robotics, it fit very well that particularly our propulsion people, John Brophy, Jay Polk and others, have continued to push the state of the art in the propulsion area using lithium ion propulsion as one of the ways to accelerate the charged lithium particle through a magnetic field to then accelerate it at the back, to get very high specific impulses. These types of specific impulses, and to kind of put it into perspective, were things like if we were able to enable this technology, the goal was to have it go out to, like, say, 40 AU, a spacecraft, in about 1 year. We had other people that were discussing, I'm not sure why you'd want to send an astronaut to Jupiter, but you could send an astronaut crew to Jupiter with this type of system. Like I say, this was a part of a NIAC, an innovative concept that where we were trying to really push the technologies in a lot of different areas to try to make it truly a game-changing technology. So it was very interesting and encouraging that this has continued, to be funded. It was funded for multiple phases in the NIAC arena, but has also been funded by others within NASA to try to see if we can bring this to fruition. And as you might guess, as you get further and further out to 40 AU and beyond, certainly even your laser beam spreads out beyond the size of your receiving spacecraft. But that's actually one of the things that we were looking at to use to, as we were talking about earlier, being a friendly and desired target, we're able to provide feedback. So you can imagine, even if the spacecraft started to drift out of we'll call it the beam, then those portions of the solar, they'll say the portions of the laser conversion system that were not being hit would show a drop off in power. And that could be used on board as a way to try to correct the spacecraft, to, say, literally move it back into the beam that is laid out there. In addition to, if we needed to do so, we could have the laser pointed, corrections made to do whatever's needed to get it to its destination target.
Bill,
Yes.
we we're about at the next time. So can you please finish
Yep,
up so we can get to our breakout
that
session?
sounds good. Sounds good. Let's go to the next one. Here we are seeing some of the comparisons done for the solar photovoltaic versus power beaming for some of the other distant targets, where we're making comparisons here and advantages of the two, and we're getting some details here on the efficiencies that are assumed going into this. The next one, next slide. We're looking at here Miranda, certainly one of the moons around Uranus, as being another target where we could then power beam down to explorers or to different types of robots that could do the exploration there on Miranda. And then the next one is the last slide, and the conclusions, where we're looking at power beaming, and certainly involves the wireless transfer of power, and it could certainly be a revolutionary new way to explore space, as we covered. The power beaming has this potential, to be an alternative solution of empowering these things as opposed to sunlight, as well as a source of power for robotic, permanently shadowed regions, essentially like RTGs, they power things where the sun don't shine. And finally, the power beaming level of 12 kilowatts per square meter is very impressive as a demonstration. And that's it.
Thank you very much, Bill. And you're around tomorrow for the more technical day. There'll be plenty of questions that we can all work through together, both during the breakouts that we have coming up, as well as during the breakout session, which is going on tomorrow as well.